Hey, welcome back. This lecture is going to be introducing the idea of graphs, which you have presumably seen in some sort of a discrete math course. I'll review the important part. And then we will be discussing the two fundamental applications of the two fundamental implementations of graphs. And then from there, on the next lecture, we'll be looking at our own more advanced implementation, which is sort of a takeoff of one of the things we'll look at today. So, as you have hopefully seen before, we talk about the idea of a graph. Mathematically, it's simply the notion of two sets, a set of vertices and a set of edges. And so commonly we describe the graph as a set of vertices and a set of edges, where V is some sort of set of vertices, say A, B, C, D, and E, and then your edge set is pairs of vertices. So I have here maybe AB, and I have CB, and I have DA, and I have EB. And so the graph starts to look like this, where I have here A and B are connected, and C and B are connected, and D and A are connected, and E and B are connected. And then maybe also I have an edge, E and D. And they're connected like that. And you might also, we're going to follow the books convention. If you look in chapter 12, if you're unfamiliar with graphs, you definitely want to read the beginning of chapter 12 in the book. There's a lot of various definitions as you leaf through section 12.1. And we're going to be discussing some of 12.1 today. But 12.1 also goes over a number of different definitions as they kind of describe various terminology about graphs. And so when we deal with the idea of a directed graph, that means we have direction on our edges. And so we're going to follow the book's convention of directed graphs will sort of describe in angled brackets. And so we could have said, well, forget that edge set. If we had written the same edge set like this, A comma B in angle brackets, C comma B, D comma A, E comma B, and E comma D, all the same edges as above, but in angle brackets, we're implying there's a direction that A is the source and B is the target, and so that there's a direction there. There's an edge from C to B, there's an edge from D to A, there's an edge from E to B, and there's an edge from E to D. And so we have here an undirected graph where the edge basically goes in both directions, and we have here a directed graph where there's a definite source and a definite target to the edge. And so we talk then about going from the source to the target, but you can't go the other way backwards against the direction of the edge. And so there's a number of other pieces of terminology as well. They're useful, neighbors and directed paths and things like that. And you should read over section 12.1 in the book if you're unfamiliar with that terminology. I'm going to assume you've been through some discrete mathematics course before where you'll learn basic tree and set and graph terminology. And so I'll leave that at that. We're not going to test you on it, but anyway, you do need to know things like what a directed graph is. So take a kind of a brief glance through that just to familiarize yourself with the basic definitions. Our concern here is implementing a graph. And so we have a graph, for example, like this, where I'm just going to pick some graph of blue. We have here, say, A and B, and maybe C points to B, and we have D pointing to C, and also D pointing to B, and we have here E, and there's a graph there. And we may even go ahead and throw some direction on it, but I'll do that in a moment. And one possible implementation for a graph is known as an adjacency matrix. And the primary concern of the adjacency matrix is to keep track of the adjacencies of the vertices. Our concern is that we want to know that we have an edge from one particular vertex to another particular vertex. And so if these were directed, if they're undirected, we have an edge from A to B and from B to A. If this was directed, we maybe have, let me just throw in some random directions here, and then maybe we have something like that. Here I have an edge from A to B, from B to C and from B to D, from C to D, from E to D, and from E to A. And so what I would do for an adjacency matrix is I would say, well, I'm going to have an array. My concern is looking up the adjacencies. So I want an array because if I have an array, I can look things up very quickly. And we'll assume for the moment that we have the ability to go from vertex label to array index very quickly. So conceptually, we will write the vertices as the indices of the array, and we're assuming here that there's some sort of quick conversion from our vertex. We can go from the name and hash on an index, or perhaps the vertex itself, if we store it as an object, holds some key inside it that's the appropriate array index, or whatever. We're not going to worry about those details now. That kind of thing can be done. We're just going to concern ourselves with assuming we have the indices corresponding to the vertices we're talking about, how are things arranged. And generally, when you pick out your row, that's the from, and the column is the to. So here we say we have an edge from A to B. We have an edge from B to C and from B to D. We have an edge from C to D. And we have edges from E to A and from E to D. And the idea here is we store 1 if the edge exists, and we store a 0 if not. And so that's the simplest form of the adjacency matrix. We simply say, looks like it says adjacency to matrix. The simplest form of the adjacency matrix simply stores a 1 whenever there's an edge from that vertex to the other vertex. And then in all other places, we would store 0. And so there's your basic adjacency matrix implementation. Now, when dealing with this, then that means that there's the speed advantage here. As we said, is one of, if you have 2 vertex indices, you can very quickly tell whether they're adjacent or not just by reading the 2 cells. And of course, if you have both indices, you can get the cell in constant time. And you quickly read whether that cell is 1 or 0. In addition, I can add a new edge very easily. If I want to add an edge from A to C, I simply find the A to C edge and change that to a 1. And likewise, if I wanted to remove that edge, I would find that A to C cell and change it back to a 0. And so it's very easy to make changes to the collection of edges, simply by changing 0s to 1s or from 1s to 0s. Similarly, if we were storing weights on our edges, and we'll be looking at an example of this very shortly in a few lectures, if our concern was storing weights on our edges, so for example, if I had a 10 on this edge and an 8 on this edge, modeling perhaps a transportation network, and I could put weights on the other edges too. I'm just going to use this to illustrate the idea. If we're modeling a transportation network and we're trying to say, well, now I want the edge to indicate how many miles long the road the edge represents some road, and I want to indicate how many miles long the road is. Well, if I only have to store one piece of numerical data, I can say, well, I'll store the actual weight. If I store 0 there, it means there is no weight, or in other words, the edge doesn't exist. And if I store a positive number, then that positive number would be the weight of my edge, the number of miles. And so from B to D, I'd say here we have, say, 10, and so on. And I could change those. So if we only have to store one integer, the weight of the edge, for example, I could store that integer instead of 1 or 0, and then I could assume if the 0 is there, that means the edge doesn't exist, and a positive number is our positive integer data. More generally, if I wanted to store an entire record rather than just one integer, what I could do instead here would be to say, let's say E to A, there's a whole bunch, on each of these edges, there's a whole bunch of information I'm concerned with finding. And so when I go from E to A, that represents the road from Chicago to St. Louis, and I want to know how long it is, and what construction company built it, and what kind of concrete it's made out of, and what other towns are along the way that aren't the major cities represented in our graph, and where the best restaurant is to eat, and all sorts of things like that. Well, then that's more than I can fit in one integer cell. Instead of having a huge, large, massive information in each of these cells, which expands the size of the array, what I could do is simply say, Instead of storing 0, I'll store null, and instead of storing 1, I'll store a pointer to some information record. I could, of course, have an array of information records as well, but that would mean anytime the edge didn't really exist, we'd have to store an information record with all default nonsense information, and that could take a lot of space. If I had one of these huge records in that cell as well, holding a bunch of garbage, default meaningless data. So instead, if I have a large amount of information to store in each cell, I might go ahead and say, I don't want to allocate all that information just to hold nothing. I'll instead of having 1 or 0 in the array, I'll have null or non-null. And it's still very easy to determine adjacency data from that, because I can determine whether a pointer is null or not null just as easily as I can read whether it's 0 or 1. And yet, if it's not null, then that value that it's holding that's not null is also a legitimate address to some node that holds a lot of helpful information. And so we could do things that way as well. Instead of having the adjacency matrix hold 1s and 0s, we could have the adjacency matrix hold nulls and legitimate addresses. And I can just as easily tell whether it's null or not as whether it's 1 or 0. And then they have the added bonus of the address would point to a helpful record of information if I had a lot of information. If all I have is the integer 1 or 0, there's no need to do the extra dereference. Just go ahead and store a 1 in the cell. My mingled graph here aside, you'd be consistent all the way throughout. You'd always be storing weights, or you'd always have pointers to records. You wouldn't say, oh, sometimes it's 1 or 0, and sometimes it's a weight, and sometimes it's a pointer. I'm just sort of showing things on the same diagram, so I don't have to redraw it over and over again. But you'd be consistent. You'd have a consistent use throughout, either all 1s and 0s, or all pointers and nulls, or whatever. But anyway, those are a few variations in the adjacency matrix. The point is simply to have a two-dimensional array holding connection data, and then what we store at that connection data spot is up to us, whether it's simply a bit or an integer indicating that the edge exists, or whether it's a pointer to some edge information record, or whether it's an actual positive number weight, or whatever it is we find helpful to store. And there's as many variations as you can think of. But the essential idea behind this is that we've got a cell for every possible connection to A, and therefore it's possible to look up connections very quickly and tell very quickly whether that connection is signaled as existing or signaled as not existing. Now there are a few interesting points to note here. Firstly, note that if this had been a undirected graph, which is what I had originally, and let me draw the original graph I had again. If I have here A, B, C, I'm sorry, that was E. Here I had C and connected to B and D, and that was my original graph. Note that if I'm going to draw the information here, I'll have each edge represented twice, because basically if we're going to deal with a undirected graph, we can sort of think of each undirected graph edge as being two directed graph edges, one in each direction. And so I'm saying A is connected to B, and also B is connected to A. B is connected to C, and also C is connected to B. B is connected or adjacent to D, and also D is adjacent to B. C and D are adjacent to each other. E and D are adjacent to each other. And A and E are adjacent to each other. And everything else would be a null. Sorry for the sort of slanted lines here. I should have drawn that a little nicer. Anyway, as you might be able to tell, this graph is symmetric across the diagonal. That is, A of I, J is always equal to A of J, I. And if you may remember way back in the sparse array lecture, I had mentioned that one possible implementation for a sparse array, or one situation, one kind of default element you might have, would be a default element where the elements could be calculated from other elements. And here's an example of that. If I really wanted to save space with the adjacency matrix, if I knew it was an undirected graph, all I would really need to store would be the top half or the bottom half of this. I wouldn't need to store everything, because if I want to know about the connection from C to D, I could get that very easily by just reading the connection from D to C, because it would be the same information in both cases. The assumption is when you have the edge going, both ways, from C to D and from D to C, then you have the same values stored in both the C to D cell and the DC cell. And so that's the idea here, is for an undirected graph, and this is always the case, for an undirected graph that leads to a metric matrix, if we're using the adjacency matrix implementation. And so that's just sort of a point of interest that you might keep in mind. The other thing worth mentioning is that one of the downsides of the structure. And one of the downsides of this setup here is that it's going to take a while to insert a vertex. Because what I have here is an array. I've got a two-dimensional array, but if I want to add a sixth row and a sixth column, that's now going to necessitate expanding the array. And so I can say here, well, if this is my existing array, I would now need to expand that. And what that essentially requires is, if this is my existing array, I'm needing to create an array of one larger row, one larger column, and then traverse all of these and copy them into here bit by bit. And now I've got that available. So if I've only got this part here, this is 5 by 5, and I want a 6 by 6 array, I need to traverse the 5 by 5 part, copy it into the new 6 by 6 array, and then it gives me index 6 here to make use of. And the idea there would be, if out of the blue I just sort of inserted a vertex F that wasn't connected to anything yet, but I at least had a vertex F, I would then need the space to be able to connect F to these other vertices in the future. Sort of like if we build some city on an island, and then we might build roads to the mainland or something like that. So now we've got room for that vertex F for the row and the column. And so this is going to be a V squared proposition where V is the number of vertices. Typically we use V for the number of vertices and O for the number of edges. The book uses N for the number of vertices and E for the number of edges. To me, there's no reason not to use V for vertices, so we'll do that. So the book says, if something is N plus E, we'll say V plus E, and so on. So anyway, that's the idea there. Now you could also have used the strategy we talked about before, where for a stack we had said that you could indeed go ahead and if you're going to store a stack as an array, you could allocate more space than you need, and then just use part of it. And as your usage expands to fill the array, you then allocate double the size. You're using all this now, but now you have room to grow, and that required a copying. You could also do that with graphs, but keep in mind you'd be using now 4 times as much space, not 2 times as much space. If I wanted to say, for example, here, I'm going to have here a 20 by 20 array allocated. If at some spot I'm only using 10 cells at a time, well that's what I'm using. I now have room to grow an 11th vertex and a 12th vertex and so on. But all that memory, this probably should have been drawn to scale a little bit lower than I did, but anyway. 20 by, that doesn't quite look like a 15 by 20 array, but anyway. This would be, cell 13 and cell 14 and cell 15 and so on. And we have room to grow into this array, but we're using 3 chunks in addition to the one we're using. And so the idea here is we would need to store 4 times as much memory, because for every cell we have, if we have n cells, we need n squared memory. If we have or for n vertices, we need n squared memory. For 2 times n vertices, we need 4 n squared memory cells, and that's what we are facing here. So in that case, your decision whether to have your extra space allocated ahead of time or not might change. And it might change too depending on whether you expect to insert a lot of vertices all the time or not. But anyway, those are some of the issues involved with the adjacency matrix. As I said, the central idea, though, of the adjacency matrix, whatever variation you might use, the central idea is one of saying, at a given from vertex, I have all the 2 vertices represented. Whether like that, or whether it's, like I said, for an undirected graph, you might have only had the top or bottom portion of the array stored. But the idea would be I have the ability to traverse across all my neighbors and say, A is not connected to A is connected to B, A is connected to C, A is not to D, A is not to E, and so on. And so one other thing I might mention, you notice I have zeros on the diagonal. If I had self loops, then those might have been 1s, but generally you tend not to see that. And so you usually will see 0s in those diagonals, though sometimes you might see self-loops. But the idea here is that the adjacency matrix will store all of those values, and you look over them one by one and decide, is this in the graph or isn't it? And so that leads to another downside of the adjacency matrix. It's got some really nice positives in terms of being able to do with edge manipulations and edge lookups very quickly. But there are many graph algorithms, and we'll be seeing some of them over the next few lectures, where our concern is to find all the neighbors of a vertex. In other words, for example, here, forget this loop I just added, all the neighbors of A. So put this back to 0. And I say, what are the neighbors of A? What vertices are adjacent to A? And I say, well, I've got B and C. B is a neighbor of A and C is a neighbor of A, but there's no edge from A to D, so D is not a neighbor of A, and there's no edge from A to E, so E is not a neighbor of A. And you can see that here. You've got 0, 8, 1, 0, 0, or whatever, our mix of stuff here. The point is that we have 0 values at A, D, and E, and we have non-zero values at B and C. So if I was trying to traverse across all the neighbors of A, I have to look at 5 cells here. I have no idea of knowing which cells are neighbors and which aren't. I have to individually inspect each cell to determine whether each cell is a neighbor or not. And that can be difficult to do. I shouldn't say difficult, but it can be time-consuming to do if you happen to have a lot of vertices. What if we had 200 vertices in the graph and each vertex had at most 3 neighbors? I'll have rows of 200 zeros, they won't all be zeros, but rows of 200 cells, only 3 at most of which will be non-zero. And I'll have to spend time looking at 197 zeros to find the 3 cells that are not 0. And so as we have more and more vertices, if the graph is sparse, then this will be firstly a waste of memory. We'll be storing most of these zeros. And secondly, for applications which rely on saying for all neighbors of a given vertex, blah, 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 do whatever, then we're going to have to look through all the vertices to find the neighbors. And it would be nice to be able to just retrieve the neighbors quickly without chewing up time looking through all the other vertices as well. And so that leads to our second implementation, which is an adjacency list. And for that same graph that we drew earlier, I'm going to draw the directed version. We can say here we have A. I guess that's the edge I added later on. These are the ones I had in the beginning. B, D, C to D, and A, or E to A, and E to D. And the adjacency list implementation, the simplest version of it has a single-dimensional array. And then off of each of these, instead of, as in the matrix, an array of 1s and 0s depending on whether you have that, whether you're adjacent to that vertex or not, we simply have a list of the things we're actually adjacent to, the things that are actually our neighbors. So A has C as a neighbor, and it has B as a neighbor. B has C and D as neighbors. C has D as a neighbor. E has nothing as a neighbor. And E has A and D as neighbors. And you can see in this graph here I've got 2, 4, 7 edges, and indeed I have 7 nodes total in the nodes of the adjacency list. And so the advantage here is now if I want to know the neighbors of A, in 2 lookups I see them. I follow the pointer at cell A and I get C, and I follow the pointer at cell C and I get B. And then the B's pointer is null, and so I know there are no nodes following that, and therefore no further neighbors of A. And likewise at B, there are 2 neighbors. At D or C there is 1. D has no neighbors, and A has 2. And I can find each of those neighbor sets very quickly and traverse across it quickly without chewing up the time searching through a bunch of zeros. For example, for D, I know there are no neighbors right away. I don't need to look through 5 zeros to determine that. And of course, in a more realistic graph that was much larger, I'd have to look through 200 zeros or something like that to find that there were no neighbors, and that would be a pain. And so that's one of the advantages here of the adjacency list is we don't have to chew up a lot of time searching through vertices that aren't our neighbors. We just look at the neighbors ourselves. And since so many graph algorithms rely on that, rely on the notion of saying, for all neighbors of a vertex, do some action, we'll find that the graph algorithms we talk about for the next few days are going to tend to be, we're going to assume we are using the adjacency list implementation when we talk about the implementation, unless I say otherwise. Because the adjacency list implementation will tend to be faster because we'll be able to look at all our neighbors quickly, or at least it'll be faster for sparse graphs. Sparse graphs being graphs where the number of edges that exist is much less than the possible edges that could exist. Here I've got 7 edges, but if I've got 5 vertices, I have 25 possible edges. Each vertex could point to any of the other vertices, including itself. So I've got 7 edges out of the possible 25 in a directed graph. And so that is a sparse graph. On the other hand, if I had 24 out of the possible 25 edges, that would be a little bit more dense. And so in that case, these lists would tend to have almost all the other vertices in them anyway. And in that case, the adjacency matrix won't be really any slower than the adjacency list for looking at all the neighbors of a vertex. When we talk about traversing over these structures, which will be important to us, for say printing out each of the adjacencies one by one, if I want to traverse over the adjacency matrix and print out one by one, A is adjacent to B, A is adjacent to C, B is adjacent to C, and print out only the adjacencies and nothing else. This is going to require searching across the array row by row to see which cells are active, and then print out that there's an adjacency between those 2 vertices. And so traversing here is going to be order v squared. Because we have v squared cells, we need to look at every single one of them to know which pairs are adjacent and which ones aren't. In the adjacency list representation, we only have to look at the existing nodes here. So at first glance it looks like, well, there's one of these nodes for every edge. You'd think traversal would be order E. That's not exactly the case because you also have to look at vertices even if they're null. So if I only had A connected to, if I had 200 vertices and no edges, I'll still need to read the null pointers one by one down the array of vertices. And so our traversal time here is thought of as order V plus E, which is sort of linear time for a graph. When an operation takes time equivalent to the number of vertices plus the number of edges, for all practical purposes, that's our graph linear time. It's linear in vertices and linear in the number of edges. And so that way we say, well, if there are no edges, we still take order V time to look at the null for each cell. And if we have a large number of edges, in fact, if we have all possible edges, then E would be equal to V squared, and then that would be no different than the adjacency matrix. Because whether we're traversing down the array cells one by one, looking at all the vertices, or whether every possible node exists in every one of these lists, you're still looking at the same number of cells. And so certainly this ends up being order V plus V squared, which is order V squared if the graph is dense. So if it turns out that E is equivalent, roughly equivalent to V squared, that's when we have a dense graph, and that's when the traversal time here would be no different than the adjacency matrix. But if E is much less than V squared, then you have a sparse graph. And in that case, the V and the E factors both count here. And that's really all there is to say about the basic implementations. There's, like I said, there's a number of variations on the adjacency matrix. We talked about a few of them, but it's still essentially an adjacency matrix. The core idea is you can look at, you have a cell for every pair, and then you have some piece of data indicating the edge exists or not at every cell. The adjacency list stores only the edges that exist, and if the edge isn't in our collection, it's assumed not to exist. Undirected edges, if you had an undirected graph, would appear twice. You'd have an A to B connection and a B to A connection. So here we have 7 nodes because we have 7 edges. If we had 7 undirected edges, then each edge would appear twice, one for each order of the vertices. So you'd have, an A to B node and a B to A node, and so you'd have, for 7 undirected edges, 14 nodes in the adjacency list. And you can draw that out yourself if you want. But definitive feature of the adjacency list is that we have the list of our neighbors off a vertex rather than a list or an array of all possible neighbors and then determining whether each neighbor really is a neighbor or not. Here we have a list of only the actual neighbors we have, only the vertices that are actually adjacent to the vertex we're looking at. And so that's the distinguishing difference between an adjacency list and an adjacency matrix. Likewise, there are a huge number of variations on this idea, one of which we will look at in detail in the next lecture because it's how our own graph class is implemented. But the idea behind the adjacency matrix and the adjacency list, those are sort of the core two graph operations, and that's the distinguishing feature between them, whether you're storing information about all possible neighbors or just the neighbors you actually have. And so that's it. That's it for the basic graph implementations. The next lecture we'll talk about the graph class we use and sort of more generally discuss the kind of interface we might build for a graph class. But first I wanted to cover the core implementation ideas of the adjacency list and the adjacency matrix. So that's it. Like I said, this one's kind of small, this lecture, and we will see you next time. Take care.